Hi, I'm Fleshed Out Thoughts, and I love fleshing out thoughts for extended periods of time. And I'm building a full stack e-commerce platform for digital products and software services with Next.js and Supabase. This series is about the architectural decisions behind the platform, what I built, why I built it that way, and what I do differently. Today, we're going to be getting into data management for my e-commerce platform, classification, retention, and GDPR. Data management is one of those topics that sounds like a compliance overhead until it's actually a problem. Then it's an expensive problem. A developer adds detailed logging that captures email addresses. 6 months later, a user requests erasure under GDPR, and you're manually scrubbing 90 days of compressed log archives. A developer stores just the last 4 digits of a card number for display convenience, and the security auditor flags the entire orders table as now being in PCI scope. A user requests account deletion, the developer deletes the profile row, and the user's email address remains in 6 other tables. None of these are hard problems to prevent. They're problems that weren't thought about at the right time, before the log statement was written, before the column was added, before the deletion logic was implemented. This video is about building data management decisions into architecture from the start. So why does data management matter? Well, there are 3 failure modes, each with a real financial consequence. The log that became a liability. If a developer added a detailed logging for debugging email addresses, IP addresses, order contents, 6 months later, a user requests an erasure. The logs are in 90 days of compressed archives across 3 environments. The cost, a compliance violation plus manual log scrubbing at professional services rates. The alternative, building with SafeLog from day one, which never puts raw PII in logs. Secondly, PCI scope creep. If a developer adds a card last 4 column to the orders table for display convenience, the security auditor flags it. Now the entire orders table is in PCI scope. Every query, every backup, every export must comply with PCI DSS. The cost, PCI compliance for a table that didn't need it. The alternative, fetch last 4 from Stripe's API when you need to display it. Never store it. The orphan personal data. A user requests account deletion. The developer deletes the profile row. The user's email address remains in order events, email outbox, coupon applications, and years of structured logs. The cost, incomplete erasure is a GDPR violation. The alternative, design the erasure function to pseudonymize, not delete. Data classification, there's 4 tiers. The SVG shows the 4 classification tiers applied to the profiles table, each column color-coded by tier. Critical, never store if avoidable. If stored, encrypted at rest, access logged, rotated regularly. PCI DSS applies to payment card data. Examples, payment card data, auth tokens, API secret keys, TOTP secrets, sensitive, encrypted at rest, Supabase default, access restricted to authenticated owner, subject to GDPR right-to-erasure, pseudonymize, on account deletion. Examples, email address, full name, shipping address, date of birth, internal, standard access across via RLS, retained for business and legal purposes. Order IDs and purchase amounts are financial records. They must be preserved even after account deletion. Examples, order IDs, purchase amounts, product IDs, subscription status, public no access restrictions, served to unauthenticated users, no personal data, CDN cacheable. The examples are product names, prices, published blog posts. Classification drives every downstream decision. Retention period, encryption requirements, across control design, erasure behavior, and audit logging. Classify every field at schema design time. PCI scope. PCI scope is triggered by the presence of cardholder data in your system. There are 5 specific things that pull you in. Storing card numbers, even encrypted, even hashed. Storing CVV codes. PCI DSS prohibits storing CVV after authorization. including in logs, storing expiry dates in combination with the card number, storing the last 4 digits, not the full PAN, but still classified as cardholder data, putting any table that stores it in scope, and receiving card data in transit. If your server ever sees the row card number, even briefly, that transmission path is in scope. My current approach, Stripe's hosted payment fields. The card data enters Stripe's environment directly. It never touches my server. I store 2 opaque identifiers, Stripe Customer ID and Stripe Payment Method ID. Both are references into Stripe's system with no cardholder data content. This holds me at SAC A, the simplest PCI compliance level, essentially attestation that all cardholder data is handled by PCI compliant third party. The last 4 digits trap. Don't store it. Stripe returns the last 4 in the payment method object. Fetch it from Stripe when you need to display it. The API calls it fast. The PCI implication of storing it yourself is not worth the saved round trip. Encryption strategy. Supabase provides 2 encryption guarantees out of the box, AES 256 encryption at rest for all database data, and TLS 1.2 or higher for all connections in transit. A compromised backup file is unreadable without the storage key. A packet capture on a database connection reveals nothing. These 2 guarantees cover the vast majority of what GDPR requires for sensitive personal data. Supabase Vault is a dedicated secret storage mechanism within Supabase, encrypted at rest with a separate key from the main database encryption. I use it for TOTP secrets that must be stored server-side. Application layer encryption. Encrypting a value in your application before it reaches the database. This is only needed when a database admin with direct access should not be able to read the plain text. The use cases are pretty narrow. TOTP secrets and recovery codes where the security model requires the value to be opaque to infrastructure itself. For email addresses and shipping addresses, database level encryption is sufficient for GDPR. Adding application layer encryption to those fields increases query complexity. Encrypted values can't be indexed or searched without a corresponding security benefit. Retention policies, 7 data categories, each with a specific retention period and reason. Financial records, orders, invoices, line items, 7 years. UK Company Act requirement. HMRC audit trail. Cannot be deleted regardless of erasure request. These are legal obligations, not operational choices. Personal data, email, name, address, duration of relationship plus 30 days. GDPR Article 5. Personal data must not be kept for longer than necessary. The 30-day grace period handles the account closure processing window. Session data and auth tokens. Token lifetime only. Supabase manages this automatically. Audit logs. 2 years. Security incident investigation and regulatory requests, pseudonymized. No raw personal data, so no erasure obligation. Support tickets and communication, 3 years. Evidence for disputes. Pseudonymize after ticket closes if the user requests erasure. Application logs, 90 days. The operational debugging window. Because SafeLog ensures no raw PII appears in logs, there's no erasure obligation for logs. You can't erase what is not there. The tension between the 7-year financial retention requirement and the GDPR erasure obligation is resolved by pseudonymization. The order record is retained. The personal data attached to it is replaced with placeholders. Right-to-erasure. A naive erasure implementation deletes the profile row. What remains? The user's email address and order events payloads in the in the email outbox table, in coupon application records, in support ticket threads, and in audit log. The user is not erased. Their personal data that is scattered across 6 tables. That is a GDPR violation. The correct approach is pseudonymization. Replace PII in the profile row with placeholders. The email becomes erased. User ID deleted. The name becomes deleted user. Phone and address are set to null. Erase that is set to the current timestamp. The profile row exists as a structural record. The user ID foreign key references in the order table remain valid, but the personal data is gone. Then revoke all sessions with Supabase auth admin delete user. The user can no longer authenticate. What's preserved? The order history with line items and amounts, financial records with a 7-year retention obligation. What's erased? The personal data that made those records identifiable for order events and email outbox. Payloads that may have contained email addresses. This is where SafeLog and structured data design pay off. If the payload only ever contained user ID and no raw email addresses, there's nothing to pseudonymize in those tables. Non-production data. The hidden risk. Production data copied to staging for realistic testing creates a GDPR obligation in your staging environment. Most teams ignore this. That's a compliance gap. The typical workflow. Production database copied to staging for debugging. Staging now has real email addresses, real names, real order histories. Staging is accessible to the entire development team, often with weaker security controls. A user requests erasure from production. Production is erased correctly. Staging still has their data, unreachable by the erasure function, unknown to the support team handling the request. The same problem exists locally. Let me just copy prod to staging to debug this issue. Now, real email addresses are in the developer's local database, in their IDE's query history, in their SQL editor's autocomplete cache. The solution? Anonymize seed data with realistic volume and structure. I use Faker.js to generate 500 realistic-looking users with plausible email addresses, names, and purchase histories. All relationships preserved. All volumes realistic. Zero real personal data. No GDPR obligation in staging or development environment. Schema evolution. Every new column added to the schema is a new data management decision. The mistake is treating it as only a technical decision. Before writing the migration for any new field, run through 6 questions. What is this classification? Critical, sensitive, internal, or public? Is this PII? Does it identify or could it be used to identify a natural person? If yes, GDPR applies and erasure must be designed. Is this in PCI scope? Does it relate to a payment card? What is the retention period? And who enforces it? Does erasure affect this field? Update the erasure function if yes. Who can access this? Update RLS if needed. The data map is the living document that records these decisions for every field in the schema. The format? A Markdown file in the repository, updated in the same PR as the migration. It becomes the GDPR Article 30 record of processing activities. This is required for regulatory audits and data subject access requests. When a user asks, "What data do you hold about me?" the data map is how you answer accurately. Without it, the answer requires manually auditing every table, which is expensive, slow, and error-prone. What I intentionally kept simple. 4 deliberate simplifications with explicit upgrade triggers. No automated retention enforcement. Retention periods are documented. Enforcement is currently manual. The upgrade trigger is when data volume makes manual review impractical, or when a regulatory audit requires demonstrated automated enforcement. No consent management platform. I collect only data necessary for the service. The update trigger is adding market automation, personalization, analytics that require granular consent tracking per data category. No data protection officer. I'm below the threshold requiring a mandatory DPO, not a public authority, not systematic large-scale processing. The upgrade trigger is if processing becomes large scale or involves sensitive data categories. Erasure via pseudonymization function, implemented and tested, not yet self-service. The upgrade trigger is when user volume makes manually handling erasure requests impractical. At that point, build a self-service erasure flow in account settings. Classify first. Retain only what you must. The 4 tiers: critical, sensitive, internal, public. Classification drives retention, encryption, access control, and erasure. Classify every field at schema design time. Reclassifying later is expensive. PCI scope. Stripe tokenization keeps me at SAC-A. My server stores Stripe customer ID and Stripe payment method ID. Never card numbers, CVV, expiry, or last 4. Don't store last 4. Fetch from Stripe when needed. Retention. Financial records 7 years. Personal data relationships plus 30 days. Logs 90 days. The tension between legal retention and GDPR erasure is resolved by pseudonymization, not deletion. Right-to-erasure. Pseudonymize the profile row. Replace PII with placeholders. Preserve the order record. Revoke all sessions. The structural record survives. The personal data doesn't. Non-production data. Never use production data in staging. Use anonymized seed data with realistic volume. Production data in staging creates a GDPR obligation most teams don't honor during erasure. For a client, data management on this platform follows a 4-tier classification model. PCI scope is limited to SAC-A via Stripe tokenization. GDPR erasure is implemented via pseudonymization that preserves financial records while removing personal data. Application logs contain no raw PII. Non-production environments use anonymized seed data. I'm Fleshed Out Thoughts. I'm building a full-stack e-commerce platform for digital products and software services with Next.js and Supabase. If you're designing data management for your own platform, classification model, erasure implementation, or PCI scope, reach out. I'm open to freelance projects and consulting. The full post is linked in the description below. Data map template, erasure functions, seed data generator, and the retention enforcement cron. Next in the series, database scaling, read replicas, connection pooling, and when to shard. I'll see you there. pseudonymized.